Okay, we are going to start discussing probability. And we're going to start that with a little bit of vocab. So a probability experiment is a trial that has varying results. The possible results are called outcomes. So for example, the trial might be flipping a coin. The outcomes would be heads or tails. Or the experiment could be called flipping a coin, right? So for example, when you roll a six-sided die, there are six possible outcomes: 1, 2, 3, 4, 5, or 6. As long as it's a standard six-sided die, you're not going to get a 2.7. It's impossible. It is not a possible outcome. A collection of one or more outcomes is called an event, such as rolling an odd number. So if I said, what's the probability that you're going to roll an even number when you roll this die? Rolling an even number becomes the event, and the outcomes that satisfy that event, if we're looking for even numbers, would be 2, 4, 6. Um, The sample space of an experiment is the set of all possible outcomes for that experiment. So if we looked at the idea of flipping a coin, what is the sample space if three coins are flipped? Well, for the first coin, I could get heads. For the second coin, I could get heads. And for the third coins, I could get heads. This is one outcome of flipping three coins. It is by no means the only one, right? But it is one. So let's just kind of systematically adjust this. We could have the last one be tails. Or we could have the middle one be tails. Or we could have both of the last two be tails. Those are all of the options where the first coin is heads, right? So then I would just copy all of this, but with the first coin being tails, and that would be all of the possible outcomes. There would be 8 of them. Okay. Another way is to find the sample space is using what's called a tree diagram. It's a little bit more organized than just listing them. It helps you not to miss any. So let's say you're flipping a coin and rolling a six-sided die. So that's our experiment, to flip a coin and roll a die. How many possible outcomes are in the sample space? So the tree diagram allows us to take each event separately. So let's start with the coin flip here. So if I start with the coin flip, there are two things that could happen, right? I could get heads or tails. So heads or tails. After I get heads, I roll a die and I could get any of the 6 sides. However, I could get any of those 6 sides after I flip tails. So each outcome would be like heads and a 1, heads and a 2, heads and a 3, etc. Or tails and a 1, tails and a 2, tails and a 3, right? So there's going to be 12 total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 possible outcomes of flipping a coin and rolling a die. That would be the sample space. Okay, let's talk a little bit about probability itself. The probability of an event is the ratio of the number of successful outcomes to the total number of possible outcomes. Right? So that'd be the number of successful, meaning events that satisfy what we're looking for, divided by the number of possible outcomes, all of the things that could happen. And this is a huge definition. You're going to want that in your notes, right? And probably this little picture I drew. Probability is always a number from 0 to 1 and can be expressed in several ways. 0 means that the event is impossible. It absolutely will not happen. There are very few things in this world that we could describe the probability as being 0. Very unlikely, maybe near 0, but 0 itself means it absolutely cannot happen. A 1 means that the event is guaranteed to happen, right? Again, pretty unlikely that we're going to find a scenario that has a probability of 1, that you know it will happen. Like the idea that the sun will come up tomorrow. Most of us treat that as a guarantee. Is it actually guaranteed? No. I mean, we don't know what's going to happen to the sun tomorrow. We have a lot of science and a lot of research that suggests it's going to be just fine for the next however many thousands or millions of years. But the sun could burn out. Um, I would consider that to be probably the highest probability thing we could talk about. I'm sure there's other examples like that. Um, but I would hesitate to say that it's 100% likely. It's, 99.99999, but it's not technically going to be guaranteed. Everywhere in between is what we're going to be talking about most of the time. Whether something's unlikely or likely determines on how close its probability is to 1. If it's right in the middle, if it's a 50-50 chance is what we call it, right? That means its probability is 50%. It is equally likely and unlikely. We don't know what's going to happen. We can represent this number as a fraction, as a decimal, or most commonly, as a percent. If all outcomes are equally likely, meaning no one thing is more likely to occur than the other, like flipping a coin or rolling dice, then we can find what's called the theoretical probability. And this is what I drew earlier. Theoretical probability is the number of favorable outcomes divided by the total number of outcomes. This is what we refer to most of the time when we talk about probability. We're going to talk a little bit later about experimental probability and how it's just slightly different. Okay, I'm going to keep moving. A student guesses on 4 true and false questions. What is the probability that she guesses exactly 2 correct answers? So first thing we have to assume, she's guessing, right? She doesn't have any educated ideas about these questions. They're strictly guesses. What is the probability that she guesses exactly 2 correct answers? Not 3, not 4, but exactly 2 of them right. So step 1, we need to find all the outcomes in the sample space. Figure out what are the possible outcomes. Identify the number of those outcomes that will be, quote, favorable, which ones give us 2 correct answers, and the total number of outcomes. How many are there possible, regardless of how many she gets right? And then find the probability by dividing the favorable outcomes by the possible outcomes. So I've kind of done some of this work already. Here are all of the outcomes. We're using I's and C's for incorrect and correct. So incorrect, all 4 of them means obviously 0 correct. There's only one way to do that, right? To get 1 answer correct, there are 4 ways to do that. You could get the first one right, or the second one right, or the third one right, or the fourth one right. It gets more complicated when we start talking about 2 correct. She could be wrong, wrong, right, right, wrong, right, wrong, right, wrong, right, right, wrong, right, wrong, wrong, right, right, wrong, right, wrong, or right, right, wrong, wrong. Those are the 6 ways that you could get 2 questions correct. If we want to get 3 questions correct, it's exactly like getting 1 question correct, but opposite, right? So incorrect and then right. The first one could be wrong, second one could be wrong, third one could be wrong, or the last one could be wrong. And then if we want all of them right, there's only one way to do that. You just have to get them all right. So there's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible outcomes if you're guessing on 4 questions. The ones that are favorable in this case are the ones where 2 answers are correct. And there are 6 of those. So there are 6 favorable outcomes. 6 over 16, or 3/8, is 0.375, or 37.5%. So if you know absolutely nothing about a subject, and I give you 4 true-false questions about it, you have a 37.5% chance of getting 2 of them right. Obviously, each question is a 50-50 chance if you're guessing, but that's not what my question was. My question was, what is the probability you get exactly 2 questions correct? Not that you get any single question correct. The complement of an event, just a little bit more vocab here, is the set of all other outcomes. So for example, let's say we're trying to find the probability of rolling a 2 or a 3. That means your favorable outcomes are 2 or 3. The complement of that would be everything else. What are all the outcomes that are not favorable? The probability of the complement of some event is just 1 minus that, right? So if there's a 37% chance you get 2 answers right, that means that there is a 1 minus 0.375 chance that you get that everything else happens, right? So that would be what, 0.625? So 62.5% chance that you don't get 2 right. 37.5% chance you get exactly 2 right. 62.5% chance you don't get exactly 2 right. Right? Everything else. Those are the only 2 options. You either get 2 correct or you don't get exactly 2 correct. It's not necessarily 50-50, but those probabilities still need to add up to 1. Okay, so here's some yo-yos. First, you flip a coin and roll a 6-sided die. What is the probability that the coin shows tails and the die shows 4? And then for these 4, I just want you to find the complement of A. So remember 1 minus the probability. Pause the video, take 2 minutes, and then come back. Okay, let's start with number 3. You flip a coin and roll a die. What is the probability that you show tails? So we write this as probability of, and then we could say showing tails and then a 4. Okay. So if we jump back, rather than redraw this, if we jump back to that factor or that outcome tree we drew, we're looking for tails and a 4, right? So what I'm looking for is this outcome right here. There are how many total? 12. And how many are favorable? How many do we want? Just 1. So our probability is just 1 out of 12. So 1 divided by 12 is 0.083 repeating. So 8 1/3%. All right, number 4. Find the complement of A if A has a 45% chance. So if we write this as a decimal, we're going to write our answer as a decimal. So the complement of A is written like that with a bar over the A, and that's going to be 0.55. 1 minus 0.45. Number 5, the probability of the complement of A. So if A is 1/4 likely, then this one will be 3/4 likely, right? What's left over when I subtract from 1? 6. This is guaranteed to happen, so the probability it does not happen is 0, the opposite. And for 7, 0.03, so the probability of the complement of A would be 0.97, right? We're just doing 1 minus whatever the probability of A is, and that's the probability of not A. Last question. Experimental probability is based on the trials of a probability experiment. So, for example, we all know that the probability of flipping heads is 50%, right? But if I flip 2 coins or flip 1 coin back to back and I get tails twice, does that disprove that the probability is 50%? No. Just because the probability is 50% doesn't mean that it's going to happen every other time, right? It just means that if you do it enough times, it'll happen half the time. So for example, each section of this spinner shown has the same area. So we got 4 sections. It's telling us they're all equally the same size. The spinner was spun 20 times. The table below shows the results. For which color is the experimental probability of stopping on the color the same as the theoretical probability? So let's talk about that theoretical probability first. Why is my pen not working? Hang on 1 second. There we go. Theoretical should be 25%, right? Because there's 4 zones we could land in. We'll assume these lines are infinitely small, so you can't land between zones. So if we did 20 spins, how many times would you think we should land in each zone? Well, 20 times 0.25 would be 5 times. So in this case, red has the same experimental and theoretical probability. It does not mean that red is less likely than green. It just so happened that in 20 trials, which really isn't that many, it happened to land on green more. If we spun this 20,000 times, we would be far closer to our theoretical probability, right? So if you think about the theoretical probabilities and you look at the error, we had a 0 error, right? We were at +4, we were at -2 and -2 from our theoretical probabilities. If we did this 20,000 times, we might still be at 4, 2, and 2, but compared to 20,000, that's much, much closer to our theoretical probabilities, right? So experimental probability does not always match theoretical probability, but as we perform more and more trials, it will get closer and closer and closer. So the only difference between experimental and theoretical is that you're looking at the number of successes over the number of trials as opposed to the number of successful outcomes over the number of possible outcomes. You're actually counting outcomes instead of looking at what could happen. You might use experimental probability if you don't know the theoretical probability and you just want to find out. You can do a bunch of trials to see what it's getting closer to give you an idea of theoretical probability. That's it for today. I managed to keep this one at 15 minutes. Good luck. Have a great day.